Thank you. Just so you know, if you Google Department of Defense climate resiliency, you'll probably find the plan for the, because they're worldwide, and they got a big job to consider climate change around the world with all their bases, and there's executive orders for that. So,
Google what? DOD and what?
Department of Defense, climate resiliency planning, something like that, and the plan will pop up, hopefully. Well, first of all, how many people are local? Massachusetts, oh, okay, good group, yeah. New England, no, all right, excellent. So I'm gonna talk about a very specific project. This came about because of Sandy. And I'll mention that our underwriters wanted to know what we were doing about this because they saw what happened to New York. Our artery system is insured, and they wanted us to come up with a plan. At the same time, though, relatively the same time, the Federal Highway Administration put out a solicitation for pilot projects. And I call it, they're FHWA, really, and they're the federal funding source for state DOTs. They have a very good climate resilience program. So if you Google Federal Highway Climate Resiliency, you'll find all these projects around the country, and MassDOT's one of them. So this project just wrapped up a little while ago. It's about a $530,000 project, and it's rather technical. I hope I do a good job with this. And so I got to hit the down arrow somewhere. Okay, here we go. So this is just some shots of the central artery tunnel system. It's a critical link to the Boston area and New England, and it has a lot of different assets. It has these vent buildings that exchange air that are required for people to use the tunnel system. We have these ramps that we refer to as portals that traffic comes in and out of, also called boat sections. And the equipment is powered by electricity. And some of these buildings go 7 stories below grade and contain switching gear that are powered by 15,000 volts of electricity. Lighting, these fans, and so there's a lot of equipment that we're trying to protect. And so we wanted to come up with a project that we could plan with and design with. And so I hired some local folks and who had done some work in the area a lot and put together this team to do this work. Now, you've seen different presentations of what sea level rise might look like. There are various techniques for doing that. There's a still water method that people just allow water to rise, and that water flows around objects and infrastructure. It can give you, it's a good tool, it's a good first order tool for screening your vulnerabilities, and there are other models that do have some storm actions. There's this sloshed model technique that emergency planners use to see where their hospitals are in danger, where their fire stations are in danger, police stations, where people can evacuate in and out of, and that generally involves hurricanes hitting the coast. We took a different approach, and I'll flip through these slides a couple of times. So this is, the one you see on the screen now is the still water method. And this one has what we call hydrodynamics in it. And you'll see there's a little bit of a difference. There's this area here. This is the Charles River, get you orientated here. This is the Mystic up in here. And this is the Charles River Dam. And the dam functions to keep the basin free of water. They control that water of the Charles River very closely. And I'll just flip back. So that's how you can see where flooding is occurring up in this area here and back in here. This is the Charles River, and then you go back with this hydrodynamics, and it's changed a lot. It's so you can somewhat over-predict what happens to you using somewhat simpler type models. Now the model we're using is a model called AdCirc, which is an open source type ocean model that people can use, companies, whatever. And it includes ocean currents, storm surge, tides, water levels, winds, sea level rise, and river discharge, and can accommodate for infrastructure within the model. Now, we coupled this AdCirc model with this model called SWAN. It's simulating waves near shore, because when storms hit the coast, you have waves and you have tides and currents. And the good thing about this particular setup is that the two models work together and generate a single output versus taking one output from one and one output from another and fiddling them together. So this is a slicker way of doing it. And the AdCirc model creates, well, you use this grid, and you see we have Florida here, this is Cuba, and this is the area where storms generate. They get born out here in the Atlantic and scoot up here along the coast. And the grid for that area of the modeling can separate like 500 kilometers, and because you want to capture a large area. As you get closer to the coast, you start to see this darker area in here. That's where the grid gets really small. That's because you want that grid to go smaller as you get into your target area, so you can pinpoint where you want to analyze. And then we get a little bit closer now into the city of Boston. And this is where the grid gets even kind of smaller, like 15 kilometers to 5 kilometers. And you start to generate information. And we're using these terms called flood exceedance probabilities. So this is a risk type modeling. It's not like a 100-year storm. It's not like a 500-year storm. So with this tool, you assess your risk based on the mapping product setup that I'll get to. But right now, this is just the background of how this modeling technique is developed. And then this is just an oblique that shows what this grid looks like in the city of Boston. This is the central artery here. This is the Tip O'Neill tunnel that goes underneath the city. And this is the Ted Williams tunnel to the airport over here. And we have a Sumner and Callahan tunnel in here that connects Boston to East Boston. This is where our information is located. This blue line here represents an elevation that we chose where water could get to during a storm event. This is the area that we have data. City of Cambridge partnered with us. They have a very good climate vulnerability program and assessment program. They're assessing the entire city, and they wanted to partner with us to inform their studies. So all in here we have data that exists where we could get storm surge. We had a large field of data that we captured. This LiDAR is light detection and ranging. That establishes your elevations within the flight paths of these aircraft that fly over and send laser beams to the ground, bounce back, measure returns, and establish elevation. We focused on bathymetry. That's the shape of the bottom of the ocean. That helps inform wave structure. Land cover is obviously good for us. We need to know that. We need to know river flows, because when it rains or when the storm surge occurs, we have actions going on in the rivers that affect where water go. We looked at historical high water marks. Tides are very important. In this area of the country, we have a 10-foot tidal range. So we had to establish that. And we had to establish sea level rise scenarios. We needed to inform the model with flood control structures like the dams. We have 2 dams in the model. We have the New Charles River Dam, and we have the Amelia Earhart Dam for the Mystic. And we had to establish storm climatology, we called it. So the climate vectors for us are sea level rise and storms. And we have good data from Kerry Emanuel at MIT regarding hurricanes. And we took a stab at, and that's tropical is the hurricane word here. And extratropical is the nor'easter term, and we built off of a Stone and Webster model back in the 1970s, simulating nor'easters, and played with that a little bit. It needs more vetting, but we had a deadline to meet, but we feel it's pretty good. So this is some model calibration we did, and we captured high water marks from the blizzard of '78, and we matched that up with the model results, and you see where the blue arrow is there. This is when the storm occurred here. It matches up pretty good with this high water mark. So this is just a way for us to get the model working correctly. And we validated the perfect storm with tide gauges, and this happens to be in Rhode Island, and you can see where that blue arrow is. And in this particular graph, the observed is in the red and the model is in the blue, and they line up pretty good throughout. This is just a slide on how we handled the flood control work. I don't know if I can get this one to run. Yeah. So this is just a simple graphic showing how the modelers coded this information into what we were calling it the model for a long time, and I've been doing that. But we actually named it, and it's now called the Boston Harbor Flood Risk Model. And you can see the elevations going up and down between the two, showing that the model accommodates for dam pumping. So we had to assess what storms could do, how they work, and how they interact with the various tidal cycles here in Boston. Now the upper graph shows a nor'easter, and if anybody has experienced one, it can last for days, and it lasts multiple tide cycles, and they can be powerful storms. But when they come and visit us, they hover over various tide cycles, and around here, you see on the TV around Situate and all that, the reporters are out during certain times of the day and during the tide, and you can see them reacting and all that. But we know that it's bad. Now, when you look at hurricanes, which is the bottom graph, now what happened to us in Sandy is that Sandy happened to hit us at a low tide. And fine, no big deal. But what we found out was that if a hurricane came in to visit us at a high tide, we just had to prove that. I mean, it's intuitive, but we did have to prove it. And we also proved that the storm does its worst, the surge does its worst damage 2 hours before high tide. So you've got the tidal forces coming in, and then you get the storm forces pushing that even further inland. This is how we assessed sea level rise. So this is from the 4th climate assessment, and we did get some pushback from our technical advisory committee. We didn't do this on our own. We had NOAA involved, we had the Woods Hole Oceanographic Institution involved, we had EPA Region 1 involved, USGS. They were kind of all looking over our shoulder, and they questioned us a lot on using this 4th climate assessment projections, and in our minds we justified it. And we have 4 well, 4 time periods that we're studying. Present day, which was back 2013, 2030, 2070, and 2100. We did these to match up with other efforts in the area, and we are moving this effort to the coast now, and we're adding 2050. So that's just a little bit about how this was the input we used for the modeling effort. And I mentioned the word risk. We used a Monte Carlo approach to analyze the storm climatology and how it affected us into the future years. Hundreds, thousands of storms. First, we started out with 1 high-capacity cluster, which is a supercomputer, went on to 2, and we never did complete 2100. This is just a simulation that we wanted to show our administration about what the model can look like with certain weather. This happens to be a nor'easter, just a graphic to show what we're trying to analyze. And so that was winds, now this is waves, and this is from a nor'easter. And this shows what happens when this particular one, or this has some hydrodynamics in it, when some Monte Carlo, but not all of it. But you can see how it goes into up to the Charles, and the waves don't really get too bad. The Harbor Islands do a pretty good job of deflecting the waves and knocking them down. This is a 2070 hurricane, example 2070 hurricane, and you can see how it's moving over Cape Cod, right around in here, and you can see how this is water levels we're looking at here, and you can see how they're kind of growing. But this is the stuff that this model is using. Let's see. Yeah, see if I can get this one to work. Sometime. Didn't find that? Oh, okay, yeah. They didn't put this movie into the program. Okay. This is just a graphic about how high the waves can be, and they're not too big in here, but you see obviously they're pretty big out here. It's like 1 to 2 feet in here. So I'm gonna get to the maps. This is what they look like, and this is the risk of getting wet, basically, in 2013. Now I'll keep that in your brain, and we move to 2030, and this is your risk of getting wet, 2 inches of water, at least. This is a 4-point channel right here, and this is the innovation district we call here. And then we'll go to 2070, and you can just see this is in this time period. This is where the water starts to flank or overtop the Charles River Dam, so you get this risk of flooding even worse. And this is depth. This is the depth of water we're looking at, and it starts at a half a foot, and it's 1/2 foot increments as the colors go, as the color palette gets bluer. And this is 2030, and East Boston is really getting hit now. This is Logan Airport, and this is 2070. And I mentioned we couldn't complete 2100 because the computers couldn't resolve all of the equations that were requiring dry turning to wet. So we had to give up on 2100. So this is called, you saw those brackets a while back with those emission scenarios. So this is actually called 2070 high emission, 2100 intermediate high. So this is really just this is just a representative of those time periods there. This is how we use the data that we get from the model. It tells us where and when to conduct actions, and it gives you various depths of water. This is a slide that shows you how much it might cost to do. I'm highlighting these certain things here because this is an actual project we're doing. We're covering, we want to cover these portals. And so we can use that data now to inform the designs for covering these portals. And those tables I showed you was an example of local adaptation strategies. This is regional, where we can protect neighborhoods within the city. So this is on the left is current day 2030, and then the strategies increase as you get farther out in time. These are the people we're sharing the information with right now. One of the criteria of the project was that we wanted to make the information public, and anybody could use it. And the list is growing. And like I said before, we're bringing it to the entire coast, doing this. And this is one of the reasons that DOT is involved, is because funding came up earlier. We happen to have a lot of the funding to do this. The coast will cost around 1.1 million. It might go up, I don't know. We'll see. And this is, the full report is available here. What I showed you was some excerpts from the report, but if you wanted to really dive into it and understand how we did it, that's where you can get it.